none other than Shiraz from TIFR. Shiraz, hi. Shiraz is a well-known theoretical physicist at TIFR. He works on string theory. He went to IIT Kanpur, did a master's in physics, went to Princeton, did a PhD there, postdoc in Harvard. He was a professor at Harvard. Then after that, he decided to come back to TIFR. He has won lots of awards, including the Increase Prize. My only claim to fame is we were together on a debate team in school. So, had some overlap with him. Scientifically, I know nothing. He works on string theory. So, Shiraz, all yours.
Okay. So, thank you very much. Thank you very much, Arnav, and it's great to be back at CnW. The talk today is titled Hawking's Black Hole Information Paradox and is precipitated by a sad event. As all of you know, Stephen Hawking, who was a theoretical physicist, passed away last month at the age of 76. Now, Hawking was a remarkable man in many ways. Most of you know about this. Okay, most of you know that his story is remarkable in several ways. One of which, one way in which it's remarkable is that his story is a story of the human spirit. Hawking had a debilitating illness. Despite that, he did remarkable intellectual work. Okay, that's a remarkable aspect of his story. Many of you know about Hawking also because he was a great communicator of science. Many of you have read his book, A Brief History of Time. I know I read it when I was maybe 14 and I found it very thrilling. Okay, but of course, in the end, in the world of science and of physics, what counts 100 years from now, when your popular books have evaporated and what really counts is the scientific contribution you've made. So this is what this talk is going to be about. In this talk, what I've done is to pick up what I believe, and I think what most people would agree, is Hawking's most important contribution to science, to human thought. And I'm going to try to explain that contribution to you a little bit. His accomplishment is the formulation of what is sometimes called the Hawking information paradox. So what I'm going to try to do is to explain to you what the information paradox is, why it's important, and what its potential importance is for the future. This is a story that has not yet played out, and I will try to explain that to you. Okay? But in order to do that, I'm going to have to, for the first 10 or 15 minutes of this talk, take you through a tour of some basic ideas of physics so that I can coherently try to explain the nature of this information paradox to you. Okay, so let's start. We'll start at a simple place. I'm going to start by reminding you of the notion of energy. It's a basic rule of physics, one that you've encountered in high school, that all physical systems have this quantity called energy. It's sort of interesting that it's not so easy to understand what energy is. Okay, when people first started developing the notion of energy, they had a very particular idea of what energy is. And then they realized that that energy was a conserved quantity. Okay, and as the development of physics went on, that notion of energy, the notion of, let's say, the motion of particles, people realized was not conserved anymore, but you could broaden your notion of energy so as to include other things to always make it a conserved quantity. And this, in the end, is almost a defining property of energy. So energy is a quantity that physical systems have that is conserved. Now, what does conserved mean? Conserved means that the value of that energy does not change as things happen. Complicated things happen. This pointer flies up in the air and hopefully doesn't break. Okay? In that process, many things are happening, but the energy of the system is not changing. Now, it's part of the idea of energy, as I mentioned, that energy comes in different varieties. And when complicated processes happen, energy changes from one form to another, but the net value of this energy does not change. So this diagram has a little example of this. If you've got a cyclist, he's on top of a hill, he has a kind of energy that some of you have struggled through in school. It's called potential energy. when the cyclist decides to coast down the hill, his potential energy decreases because he's going down, but it's converted to kinetic energy, the energy that you're whoosh flying on your bike. Okay? So this is part of the structure of physics. You've got energy converted from one form to another, but the really important defining property, almost defining property of energy is that it remains the same. The net energy of any closed system not interacting with anything else, is constant always. Okay, this is a simple and important notion. In the middle of the 1800s though, physicists encountered physicists who are trying to understand very practical things, trying to understand how steam engines worked. Steam engines work to allow you to take heat and convert it into usable energy, discovered something else that is a bit more subtle and is very interesting. They discovered that in addition to the energy and maybe some other macroscopic characterizations of physical systems, there is another important quantity you can ascribe to a complicated enough, a big enough physical system. And that other important property has a name, it's called entropy. Okay? Now, when this concept was first discovered, people didn't really know what entropy was. It's a bit like energy, it's something. People didn't really know what entropy was. But what they realized, and this was almost the defining property of this entropy, what they realized was that whatever this entropy is, it's possible to assign it to physical systems in a consistent way, and it has the property that with time it always increases. Okay? So let's contrast this with energy, which with time always stays the same. This entropy is something with which time always increases, never decreases. Perhaps stays the same, perhaps increases, but never decreases. Okay, the claim that objects have this thing called entropy, and that entropy always increases with time, is formulated as a law of physics. It's got a name, it's called the Second Law of Thermodynamics. Okay, now I want to explain this idea of entropy to you in a little more detail. Okay, and we'll start, this is one of 3 slides in which I try to explain this to you in more detail. The understanding of what I'm going to try to explain to you was developed only over the last 100 or 120 years. I mean, it's not that old. The understanding goes as follows. Imagine doing the following thought experiment, or actual experiment. Okay, suppose you've got 2 beakers. Oh my, on this slide you don't see the hydrogen. We can just, fine, we call this vacuum, okay. Okay, imagine you have 2 beakers, and in one beaker there's just vacuum, there's nothing. In the other beaker, it's full of oxygen, full of a bunch of oxygen molecules. There's a stopper between these 2 beakers that keeps the oxygen here and the vacuum here. Great. Now I undo the stopper and I wait. What's going to happen? Well, clearly some of these oxygen molecules are going to go from here to here, and if you wait long enough, clearly, after you wait long enough, there are going to be as many oxygen molecules here as here. This is going to be the final state. Okay, now if you ask, suppose I'm going to ask you to imagine, we've drawn only like 10 or 20 dots per molecules per beaker, but you should imagine that there's plenty and plenty of molecules, okay? 10 to the power 23 molecules, huge numbers, billions of billions of billions of molecules. Now if I asked you, look, we saw one kind of motion. We saw motion in which you've got a lot of molecules here, which went to evening out the molecular distribution, and that happened naturally. Just lifted the cork, that happened. If I asked you, what about the reverse motion? Suppose I just start with this description, leave this open and wait. Will it ever happen that all of these molecules will come back here? And intuitively you can see that the answer sounds very unlikely. It's got to be doing something very special for these molecules which are evenly distributed to come back here. It's and this is correct. It's pretty lucky that this is correct. You see, because if this happened all the time, it might happen that the air in this room will suddenly rush to that corner and I would have nothing to breathe with. Okay? That doesn't happen. You know that from experience. Okay? So you see, at the intuitive level, you see that there is some sort of rule of thumb which tells you that processes happen in one direction and not the other. If you confine these molecules to small regions, they like to spread out, but the reverse doesn't easily happen. Okay? And this is basically the heart of the idea of the increase of entropy. Okay? You have to try to make this idea precise. So the way physicists made the idea precise was, I'm going to give you some words now, was to define a notion of the number of states that the system can be in. Okay, what this precisely means is not very important, but in the context of this experiment, imagine taking this this system of 2 beakers and breaking it up into small little globules of volume. Having one of the molecules in one of these globules, or having, labeling which little globules the n molecules live in, is a definition of your state. Now you can see that there are many more ways, many more states of the system for the molecules to spread out over double the number of globules than there would be for them to spread out over a small number of globules. Right? Because the particular state in which all the molecules are here is one in which all these globules here are empty. But then there are other states in which one of these is put here and another one is put here and so on. So if you have this notion of the number of states of a physical system, the number of ways in which a physical system can be consistent with some basic quantities. In this case, the basic quantities are the number of molecules, for instance, maybe the energy. It's intuitively clear that a system tries to go towards a configuration with a larger number of allowed states. Okay, this is sort of intuitively clear. This is what this experiment shows to us. Okay, and so this idea of this irreversibility, that molecules try to go even out but not the other way around, is made formal in physics by defining a notion called entropy, which is a measure of the number of states. More precisely, the exponential of the entropy is the number of states in which a system can be consistent with certain crude macroscopic requirements. And the law of thermodynamics says that systems always tend to move towards those configurations in which they have more ways to be, more states to explore, than configurations in which they have less ways to be, less states to explore. Is this clear? Okay. With this understanding, it seems reasonable that, on purely probabilistic grounds, because so many more ways to do this, that evolution takes a system from lower to higher entropy states. This is the second law of thermodynamics. Now, I want to clarify a sort of important point here, and this point will play a role through much of this talk. And this point goes as follows. Look, I have tried to give you here a description of the system in terms of crude macroscopic variables, the number of molecules in this box, and ask how many states in which can it be. And we talked about probabilities, and we encountered this law of increase of entropy, saying a system would like to go from a configuration in which it has many fewer available states to a configuration in which it has a larger number of available states. Okay? Now, this way of thinking is a consequence of the fact that we are giving a relatively crude description of our physical system. There is a better description of the system which keeps track of more fine detail. The perfect description of the system, let's imagine we're talking about a classical gas. Okay, let's put quantum mechanics aside for now. The perfect description of the system would be to keep track of the position of every molecule in the chamber. If we kept track of every molecule in the chamber, we would not have a description in terms of probabilities. We would just follow the position of every molecule in the chamber. The motion would be deterministic, and at the microscopic level, all molecular motions are reversible. If molecules can do this, they can come back. Okay? This irreversibility of motion is a property of using a coarse-grained description, where you agree to give up some information. Okay? You decide you're not able to keep track of all the positions of all the molecules in the gas. You just want to keep track of some crude macroscopic variables. When you do that, you get this effective coarse-grained description in which motion happens in a sort of probabilistic way, a sort of statistical way. And then you have the second law of thermodynamics occurring for such systems, big complex systems in which you keep track of not every little detailed degree of freedom, but sort of averages. Okay? So this is what we do all the time when we're building a steam engine, or if we're trying to understand the flow of water. We don't keep track of every molecule of water. We keep track of the density of water where we're going. Or if you're designing an aeroplane, you keep track of the density and the pressure of the air around you. All these are crude statistical descriptions, not keeping track of the position of every air molecule, every water molecule. And when you describe reality, you try to describe reality in this way, you end up with a description in terms of these averages, which, and a feature of this description is that systems have this entropy, and entropy obeys the second law of thermodynamics. Okay, great. Now, although the second law of thermodynamics applies only probabilistically, it applies as a consequence of probability. And probability is a very universal idea. It's a universal mathematical structure, universal truth that applies across various different situations. In particular, the notions of probability apply equally well to different detailed formalisms of physics. And because of this, the second law of thermodynamics is a very, very universal law. You know, this law was first formulated, let's say, in the 1850s, when everyone thought that physics was classical. By the 1920s, it became clear that physics is quantum mechanical. Quantum mechanics changed many of our notions of physics. We realized that particles don't have definite positions. We realized that there's a probabilistic fuzz in various measurables and so on. So it had much of the way we thought about physics had to be rewritten to be consistent with quantum mechanics. But there were a few things that just carried through, that just sailed through the transition from classical mechanics to quantum mechanics completely unchanged. Few laws of physics. One of these laws was the conservation of energy. One of these fantastic, beautiful, universal laws that just applies across formalisms. But another law was the second law of thermodynamics. The second law of thermodynamics applies equally well to quantum systems as it does to classical systems, just because it's based on very general ideas, the notions essentially of probability and some sort of reasonableness. Okay? Now, at the end of the last century, at the beginning of the last century, there were two major revolutions in physics, one of which was the revolution of quantum mechanics. And I've told you the second law of thermodynamics had no problem adapting to the quantum world. There was a second major revolution in physics, which was Einstein's discovery that space-time is dynamical. Okay? And much of the rest of this talk is going to be about the following thing. Sort of surprisingly, it will turn out that at a naive level, there is a contradiction between the second law of thermodynamics and Einstein's theory of general relativity. And resolving this contradiction and looking at it carefully leads to many interesting lessons. Okay? So while the second law passed through the quantum revolution sort of effortlessly, it had and is having more trouble struggling to coming to terms with the dynamical nature of space-time. And this is what this talk is going to be about. Is this clear? Any questions? Well, okay, maybe any urgent questions? Okay, great. There's one more thing I want to tell you about entropy that will play a role in what we're going to talk about later. And this one more thing is this, that entropy, the notion of entropy, it turns out is inextricably linked to the notion of temperature. Now, most people who are not engineers or scientists don't know much about entropy, but everyone knows about temperature. Temperature is how hot something is. Now, it's a feature of temperature that, one way of measuring how hot something is, though this is not what you would most generally do if you were taking your temperature to check if you have a fever. One way of measuring how hot something is to see how much energy that thing is radiating. It's a universal law of physics that hot things radiate. They radiate energy in a particular way determined by their temperature. This may not be so familiar to you, but we actually use it all the time. Tungsten bulbs, the old bulbs, worked in this way. Electricity went through a wire, heating up the wire to some temperature, I don't know exactly what, let's say 3,000, 4,000 degrees Celsius. And because the thing was so hot, it would glow, let out heat, which you felt if you ever touched one of these bulbs, and let out light, which you saw, which was the point of the bulb. In a much more dramatic way, this is how the sun works. The sun lets out radiation because its surface the sun lets out radiation because its surface is very hot. It's about 5,000 degrees Celsius, and that's why it's glowing and giving us all this light. Okay? So hot things radiate. Now what is the connection between the notion of temperature and entropy? This notion is through a formula, and if you don't understand this formula, it doesn't matter very much. But let me just say it. Given a system, I've told you that every system has an energy and it also has an entropy. Now what you can do is ask, suppose I change the energy of a system a little bit. It sounds reasonable that its entropy would also change a little bit. Now I take the ratio of the change in the energy to the change in the entropy and make the change very small. This ratio has a name in mathematics, it's called the derivative. I take the derivative of the energy with respect to the entropy, and that quantity is the temperature of the system. What this means is that there are three different quantities, any two of which are independent. You can take the independent quantities to be energy and entropy, as we did in our speech so far. Or you could take the quantities to be energy and temperature, or temperature and entropy. If you know any two, you can find the third. Okay? So to say that a quantity has entropy is the same thing as saying that it has a temperature. Of course it has energy as well. And to know how the temperature behaves as a function of energy is the same as knowing what the entropy is as a function of energy, and so many other similar statements. Okay, this is the end of my lightning review of energy and entropy and temperature. You might think this is it's a story, as I said, that had its origin in the attempt to understand steam engines better, a very practical subject. Yet it's morphed into what we believe to be a basic law of physics that applies across all formalisms and will play a key starting role in what I'm going to say from now on. I'm going to switch topics completely now to a completely unrelated topic, apparently completely unrelated topic, unless there are pressing questions or comments. Comments or questions of, so I didn't understand this. Yes?
You said the law of conservation of energy holds in the quantum realm as well.
Yes.
But doesn't that violate Heisenberg's uncertain principle of final energy?
No. Heisenberg's uncertainty principle, you see, quantum mechanics works this way. States, you can have systems in which you cannot say for sure what state a system is in. A state can be in a superposition. Now it's allowed to have states which are in a superposition of different energy states. Okay? And depending on the nature of that superposition, you get this sort of uncertainty in time. Now, the law of conservation of energy in quantum mechanics does not assert that a state has to be in a definite energy state. You are allowed to take superpositions of different energy states, but the spectrum of that superposition, the nature of that superposition, that you have something at E1, that you have something at E2 and so on, that will never change in time. Okay, so it's completely consistent with them. Yes?
In case of a light bulb where the temperature is not changing, but it's continuously radiating.
Yes.
Is its entropy changing?
Is its entropy changing? No, it's not. If you keep the temperature fixed, then the entropy is just given by this formula. It's radiating, and that's because you're constantly pumping energy into it through the electric current. Okay? So the energy that's losing is balanced by the energy you're putting in. Okay, a good question. Okay, anything else pressing? Okay, let's move on. Great. So now we're moving to what seems like a totally different subject. We're going to talk about these objects called black holes. Now, what is a black hole? Well, I gave a Chai and Wai titled Black Holes maybe a year and a half ago, and if any of you want more details and can stand hearing more from me after this talk, maybe you can go and look that up to hear more details. I'm going to have to be very, very, very quick about my review of black holes in this talk, much less quick, much quicker than I was a year and a half ago. So let me very quickly tell you what black holes are. Well, as you probably know, about 100 years ago, Einstein discovered that the right way of thinking, or the right way, as the best way we understand as of now, of thinking of the force of gravity. Okay? This force of gravity that all of us have encountered in high school, that Newton is said to have encountered when an apple fell on his head or nearby or whatever. This force of gravity, Einstein realized, was a consequence of a remarkable thing. It was a consequence of the fact that the geometry of space and time itself is dynamical. Now, what does this mean? You know, before Einstein, the formulation of physics was this way. Space and time were sort of grid, a stage on which dynamics happened. The stage was, you know, a fine stage. It allowed lots of things to happen, but it was an unmoving stage. A stage on which things happened but did not participate itself in dynamics. Just things, space is where things happen, time is when things happen. You know, Newton even had the statement somewhere, eternal space, forever unchanging, blah, blah, blah. Okay, great. What Einstein realized was that actually the geometry of space and time, distances between two spatial points, for instance, is a dynamical quantity. The stage, which we previously thought of as an inert platform to host dynamics, actually was a participant in dynamics. As things happened, it changed the shape of the stage, the geometry of space and time, and the changed geometry of space and time in turn then went and affected how things happened. Okay? This was about 100 years ago. Einstein explained all this to us in his remarkable theory, the general theory of relativity. Now, there are many things one could say about Einstein's theory of relativity, but I'm going to very quickly zoom in on the one thing that I'm interested in for this talk, which is that there is a completely remarkable prediction of this theory. One of the most dramatic predictions of this theory is the following. This prediction, which took a long time to be understood, Einstein didn't believe it for a long time. I don't think he ever believed it. This prediction is this, that there are certain situations, the most common of which are the following. Suppose you've got a star, which is 5 times, let's say, the mass of the sun. Stars at some point run out of energy. You know, stars are hot because they're burning nuclear energy. Hydrogen has been converted to helium by the process of fusion. That burning process releases energy. Now, anything that burns eventually runs out of fuel. Stars have a lot of fuel, so our sun will burn for 10 billion years totally. It's done, it's middle-aged. It's done 5 billion years, it will do 5 billion more, roughly speaking. At the end of this, eventually it runs out of fuel and cools down. So, if you are, you know, now stars are very big objects. Gravity is trying to scrunch them all together. And you could ask the question, as the great Indian physicist Chandrasekhar did at some point, what happens to stars when they burn up their nuclear fuel? Now, the point of this question is this. When stars are burning the fuel, the force of gravity is balanced by the pressure that's in the star as a consequence of its constant generation of heat. Okay? When the fuel is burnt up, this pressure is not available to you. So the star starts to scrunch together. And you can ask, what happens? What will stop this scrunching? There was a long story that, for instance, I reviewed in my last Chai and Why that I will not tell you about. The important thing here is that Chandrasekhar postulated, and it's now been realized, it's almost certainly true, I'll have some more details on this in a little bit, that when the stars are big enough, about 2 or 3 times the mass of our sun, nothing stops this process. Once they run out of fuel, bye-bye. The star crunches. This goes on until it zooms to a point and the matter seems to disappear into nothingness. All that's left behind is a big lump of warped space-time. And that big lump is called a black hole. Okay? As I said, this was initially an extremely controversial prediction of the general theory of relativity. It's not controversial anymore. Nobody doubts it, and we'll see some evidence for it in 2 minutes. Okay? There exists these.
Yeah. What do you mean by warped space-time?
What do I mean by warped space-time? Well, I'll say this with this sort of analogy. Imagine you've got a rubber sheet, and you've stretched it. So the stretched planar rubber sheet is what you think of as unwarped space-time. Now imagine taking this rubber sheet and then sort of depressing it, pushing your hand and pushing it down. So it gets some sort of curvature. This is the way you think of warping. Okay? Now this analogy is imprecise in 2 ways. Firstly, my rubber sheet was 2-dimensional. Secondly, my rubber sheet was made up only of space. This kind of warping is happening in 3 spatial dimensions, But the real imprecision is that this is happening in space and time. Okay? So this you see, when you do this rubber sheet kind of warping, you can check that something is warped by, for instance, trying to draw a triangle in this warped region. And no matter how you define your triangle, you'll find that the angles don't add up to 180 degrees because it's not on a plane. Okay? So strange things happen if you're used only to flat geometry. Strange things happen in warped geometries. In warped space-times, more strange things happen. Okay? One of the things that happens is these things are light cones bend, leading to a consequence that I'll tell you about. Okay. Great. Now, yes.
What has initiated the burning of the stars in the first place?
What has initiated the burning of the stars in the first place? It's just the fact that gravity is attractive. You see, if we're correct in our understanding of how things happened, there was a process, let's say the end of inflation and the Big Bang, which left a lot of matter all over the place. Now, gravity is an attractive force. If you think about that, you will quickly see that this statement, in a situation where there's a lot of matter all over the place, has an inherent instability about it. Because let's say the matter is evenly distributed all over space, then there's no focal point for attraction. So nothing happens. But suppose some process happens so that just by chance, there's a little more matter here than there. Because there's more matter here than there, more stuff is attracted to the place where there's more matter. Because gravity is attractive. Okay? So there's a runaway instability. Any place where because of some random fluctuation there's more stuff here than there. It's uneven distribution matter, though, but the unevenness initially was extremely small. It was almost perfectly even. But that was amplified by the attractive nature of gravity. Okay? That led to this matter being scrunched into little centers, which led to the formation of clusters of galaxies, and eventually of stars. Just lots of matter coming together, whoosh, getting very hot because it comes together like this, starting the process of fusion. Okay, so it's just that. It's a very beautiful thing and we think we understand it quite well. Yes? Yes? It's made up of nothing. It's made up only of space and time. You see, the stuff that went into forming this black hole was made up of complicated things, hydrogen and helium and neon and God knows what. Okay? But that's all disappeared. All that's left behind of it within classical general relativity is the warped nature of space and time. There's nothing inside except at the strange place called the Singularity, which we'll come to in a minute. But it's a very good question. It's a key question. It's the kind of question that leads to the Hawking information paradox. So hang on. Yes? Yes? No, it does not. It does not mean that. That's a good question. You see, there are two things happening which compete with each other. One thing is that, as we know, the universe as a whole is continually expanding. Okay, that is a tendency that takes things apart. But then there's also the attractive nature of gravity. So what basically happened was that on small scales things clumped, but on larger scales they drifted apart. So the galaxies are moving away from each other.
So the expanding nature is due to what?
Expanding nature is due to what? Excellent question. The expanding nature is due to two things. Firstly, because the universe started out expanding. And that's the main thing. Let me give you an analogy. If I had a ball, okay, this thing here, if I drop it, it falls. This is the attractive nature of gravity. But suppose I took this thing, and I won't do it, but I hurled it high up in the air, it would not be falling. Okay? Now, you might say, well, it will eventually fall. But that's not true. If I hurl it at faster than a critical speed called the escape velocity, this thing will just keep going. It will escape from the earth and never come back, despite the fact that gravity is attractive. So gravity is trying to pull it down, but if you start it out fast enough, it just keeps going. So this is the main reason for the expanding nature of the universe.
So everything moving in space is moving
Beyond the escape velocity or at the escape velocity, I have to say one more thing. Yes, but this is the idea that you start off at very fast speed, which you should think of as being at or beyond or roughly equal to the escape velocity. However, that's not the full story. This is what was believed to be the full story till 20 years ago. 20 years ago, it was discovered also that, you see, let me say one more thing. You see, when I threw this thing up, if I threw it fast enough, it would keep going away, but the speed at which it went away would decelerate, would get slower and slower and slower. This is a consequence of the attractive nature of gravity. And this is what we see in our universe so far. These galaxies have been moving away, but moving away at a slower rate for a while. However, in about 20 years ago, it was discovered that if you look closely, you find that just about now in the history of the universe, something strange is beginning to happen. The galaxies are not going away at a slower speed. They're beginning to accelerate away. This cannot be explained by initial conditions. It's some change in the equations of motion of gravity, and is likely a consequence of the fact that the equations of gravity are modified by a term called the cosmological constant, which gives you, on very large length scales, a repulsive push to the universe. Okay, there's lots to say about this subject, but I'll stop here. Yes?
Is the mass of the star that it has to become a black hole?
It's about 2 to 3 times the mass of the sun.
Okay, so
That or larger. Yes.
I thought the coal has to be 2 to 3.
What, sorry?
I thought the coal has to be 2 to 3 times.
The coal, the fuel? Coal. Yes, you're right. You're right. What happens actually when stars, at the end of stars, is that many stars, let's say something 5 times the mass of the sun or 10 times the mass of the sun, will likely undergo a supernova, which is a big explosion. That explosion sends much of the mass of the star away. So the real criterion is whatever's left behind after the explosion, okay, should be more than 2 to 3 times the mass of the sun. So it's a bit hard to say what it should start with because it depends on exactly how that explosion happens. Okay, but whatever's left behind should be more than 2 to 3 times the mass of the sun. Good, excellent. Yes.
Are singularities infinitely dense? I mean, classical mechanics would suggest they would be infinitely dense.
Yes.
But according to quantum mechanics and string theory, are they infinitely dense?
Surely they cannot be, but we don't understand them very well yet. But surely the answer must be no. Yes. Yeah, please go on. Yes. Excellent. Okay, so let's go back to these black holes. So these black holes are these lumps of space and time with, okay, now this is lump of warped space and time, but you know what's really special about a black hole is that there is a particular surface here which sharply delimits the inside of the lump from the outside of the lump. And the sharp delimitation is from the following fact. If you've got a lump inside, if you've got this lump and you take something inside, nothing that was inside that lump, not even a ray of light, can ever come outside that lump. Okay? So the boundary of this region is called the event horizon. And then inside, deep inside here, there's this very dense region that the last question was about. It's called the singularity. Okay? Much of the talk here is not going to be about the singularity, but about the event horizon. The boundary of the space of the region of no return. If you send something, you've got something inside, can never come out. The boundary of that region is called the event horizon. Now, this transparency is taken from my last chai, and why? I want to give you just a minute to try to get your head around this idea. To try to understand how it can be that there is this region of space and time from which nothing can come out. And I'm going to do this with an analogy, which was actually suggested by a question my son asked me about this, which goes as follows. Okay, consider I've got a lake, okay, which is a still and placid lake, except that at one spot, let's say in the middle of the lake, there's a sink. Water is being sucked out. I don't know why. You know, maybe there's a giant snake and I don't know why. The water is being sucked out. Okay. Now, if you're far away from the place where the water is being sucked out, you see the water is just at rest. Nothing's happening. You've got a nice, dull, placid lake. But as you go nearer and nearer to this place, water is zooming in. Now, as you go nearer, because the water is being sucked out at a given rate, as you go nearer, the water is being sucked at a larger and larger speed. Now, suppose you are a pleasure speedboatist of this lake. And you're in a boat that can go at a maximum speed, let's say 100 kilometers an hour. Okay, you're zooming around all over the lake, and you want to investigate this interesting phenomenon. So you come nearby to come and look at this whirlpool. As long as you're at a place where the speed of the water is 50 or 60 or 80 kilometers, you're okay. You can come here, turn your boat around and move away. But if by mistake you stray into this region here, this line here is the place where the water is going inside at speed faster than 100 kilometers an hour. If you go inside here, then you decide, oh no, I don't want to go deep down in. I'm going to turn my boat around and zoom back out. You'll move at 100 kilometers an hour with respect to the water. But the water is moving, let's say, at 150 kilometers per hour that way. So no matter what you do, it'll just suck you in. That's roughly what's happening in a black hole. Now, here in our lake, you could get away by adding an extra motor. Make your boat something that goes at 200 kilometers an hour. But in the universe, there's a speed limit. The speed limit is the speed of light. And if the space-time starts getting sucked towards the singularity, so to speak, at faster than the speed of light, nothing can ever get out of this whirlpool. That's what a black hole is like. Okay? A region of space-time from which nothing can ever get out. Roughly, you can think of it in this way. Okay. Great. Yes? What? Why is light stationary at the event horizon? You can ask this question this way. Suppose suppose you're on a treadmill. Okay? That's running this, that's moving that way. Okay, suppose you've got a long treadmill in, let's say, a railway station, one of these walkolators, an airport. Okay? That's moving at 20 kilometers an hour. You decide to break all the rules, you get on this walkolator and start jogging, not the way the walkolator is going, but the reverse way. Okay? You also jog at 20 kilometers an hour. If somebody from outside sees you, he'll see you just standing still. Because this is pulling at 20 kilometers and you're running this. That's what's happening at the event horizon. There is a ray of light that is trying to go this way at the speed of light, it's being pulled in at the speed of light, and just so in the end just stays. Okay? Yes, we'll have to limit this, but yes.
So if the light is stationary at this point, so with the time the amount of photons in that region will keep on increasing, right? So tiny matters comes in. So what is
Yes, there are many things to say about this, one of which things we'll have to talk about is redshift. It's a complicated question, I'll postpone it for later if you don't mind. Okay, it's a good question. Okay, excellent. The main thing to say about it is that for it to be stationary, something has to be coming out that way. Okay? It doesn't really build up. I'll postpone it for later. Okay. Okay, great. Now, black holes, it's already clear from what we've said, are weird objects. Right? What are these lumps of space and time from which nothing can ever come out? Sounds like science fiction, doesn't sound like physics. And this was the reaction of many physicists, including Einstein, to the idea that black holes exist in his theory of general relativity. He didn't like it one bit. He wrote many papers trying to explain why black holes were mathematical artifacts. Okay. However, in the 1970s, Hawking and Penrose, two at that point young physicists, proved a mathematical theorem about the nature of general relativity, whose details I won't describe to you, but whose implication was the following: that all the objections that people had raised to the idea that black holes form were actually based on incorrect mathematical analysis. If you do the mathematics correctly, it seems almost inevitable that many collapse processes, like processes of the collapse of stars, will eventually form black holes. From a theoretical point of view, this theorem, the so-called singularity theorems of Hawking and Penrose, removed all reasonable doubt in the existence of black holes in the universe. Okay? Around the same time, Hawking also, using the results of a great and not so well known Indian physicist, a professor at Presidency College who's now passed away, A.K. Rai Chaudhary, proved another theorem that will play a very important role in the rest of this talk. How important this was not clear to Hawking at that time. It was a side remark in some paper which didn't turn out to be right. But this side remark has turned out to be very important. And the theorem he proved was this: that you see, we have these black holes. They have an event horizon. I've told you about them. Now these event horizons have an area. It's just the area of the event horizon. What Hawking showed was that the area of an event horizon in time can never decrease. It can only stay the same or increase. Okay? We come back to why this is important in a minute. But before we do that, I want to convince you beyond all skepticism about the existence of black holes. We know now black holes exist not just because of fancy theorems proved by Hawking and friends and by other people. We know it from direct observation. astrophysicists have been looking at black holes with telescopes for a while. Now, a black hole by its nature is black. Nothing comes out of it, so you can't really see the black hole. But you can see its effect on nearby things. This is an artist's impression of a black hole sucking gas out of a galaxy, causing it to swirl, emit lots of stuff, light before before the gas disappears forever into the black hole. We see this kind of thing all the time. There's a guy at Harvard who studied one particular black hole for the last 25 years and who knows everything about it. You know, its angular velocity to within 2% and so on. It's really impressive. There's no real doubt that it's a black hole. Okay, but even more dramatically, about 2 years ago, this by now famous Ligo experiment, assuming all the analysis is correct, saw the following. They saw two black holes banging into each other. This bang was a dramatic event that sent ripples of gravity wave through the universe, we detected these ripples 1.2 billion light years away with this fantastic new experiment, this LIGO gravity wave detector. And by interpreting the results, we know that these black holes, we know what caused them. They were caused by the bang of two black holes, each of which was 30 times the mass of our sun. This bang was a remarkable process. It lasted about 1,000th of a second, maybe 100th of a second. In that period, it released energy. The release of energy in that period was about 3 times the mass of the sun. This is a remarkable process, but we will move on. Okay, these last two transparencies were just to say that black holes are not just something in somebody's mind. We've seen them with telescopes. We've seen them with the LIGO detector. They exist out in the real world. Nobody really knows, but the ratio of black holes to stars in the universe is likely to be no smaller than 1:1,000. Since there are about 10 to the power 21 or 22 stars in the visible universe, that means there are about 10 to the power 18 or 19 black holes in the universe. Not only do they exist, they are copious, lots of them. Black holes are all over the place. There are friends and neighbors, and we have to get to know them. Okay. Now that we are convinced that black holes exist, let's go back. Let's pretend that these last two transparencies didn't exist. Let's go back to this way of thinking. We've just encountered Hawking in the story. As a young man, he proved two theorems, both very important. The singularity theorems that assured us black holes exist. And this other more abstract theorem that told us that when you have a black hole, in time the area of its event horizon never decreases but can only increase. Named the second of these theorems caught the attention of a young Israeli physicist, named Jacob Bekenstein. And it caught his attention because he was puzzling about an apparent paradox relating to black hole physics that somehow had never occurred to anyone other than him and Wheeler and a few other people at that time, which now seems so obvious. And it goes this way. In the first part of the talk, I told you that there is a law of nature that entropies of system never decrease. The second part of the talk, I told you that there's this lump of space-time into which when you throw something, nothing ever comes out. So as far as the outside is concerned, it's just, it sucks stuff out. So Bekenstein was wondering the following. Suppose I was on a holiday in the neighborhood of a black hole and I was drinking up a cup of tea and I sort of decided in a fit of fancy to throw my cup of tea into the black hole. Now this is a cup of hot tea. Okay? And so it disappears into the black hole along with all the entropy of the hot stuff in it. Now once it's disappeared into the black hole, as far as the outside of the universe is concerned, that entropy is gone. So nobody could ever tell that that entropy ever existed. So if you were to try to calculate all of the entropy of the universe, you would find that before and after, the entropy has decreased. And after you've thrown the cup, the entropy has decreased because the cup is not there anymore. There's no sign of it anymore. Doesn't it sound like general relativity, and more precisely the existence of black holes, means that there's a tension between the laws of thermodynamics and black holes? The law of entropy increase. Now, as I told, by the time Bekenstein was doing these thought experiments, we had got used to the fact that if you have a way of thinking that conflicts with the second law of thermodynamics, you're not going to win that fight. Okay? The second law of thermodynamics had emerged from many battles unscathed, the corpses of wrong theories littered in the battlefield. Okay? So, if you've got a conflict between your way of thinking and second law of thermodynamics, you should be worried. Okay. Bekenstein was not willing to easily give up the second law of thermodynamics, but how could he resolve this paradox? And he was puzzling about this when he saw Hawking's theorem. And then he had an aha moment. He said, well, you know, entropy increase is the statement that something increases and or never decreases. Hawking has told us that there's something with black holes, namely the area of the event horizon that always increases and never decreases. So maybe entropy is going to be like energy. You remember at the beginning of the talk I told you that it might at first seem that energy conservation is violated until you realize that energy has many hidden forms. When you account for all their hidden forms, you find it's conserved. Bekenstein thought maybe it's the same with entropy. Maybe there are hidden forms of entropy which you have to account for. And maybe in particular in black holes, in the study of black holes, there's a hidden form of entropy. So apart from accounting for all the entropy that you can see in all the cups of tea in the universe, you must in addition add the area of the event horizons of all the black holes in the universe, and that is the quantity that will increase and not decrease. This was the suggestion he made. Now, when Hawking encountered this suggestion, he initially reacted to this like this was a misuse and misappropriation of his beautiful results. This he thought was ridiculous. But you know, in physics you can't just declare, no matter who you are, you can't declare something is wrong. That's a great thing about science, okay? It's not about who you are, it's about what you're saying. And so Hawking needed an argument, and his rough argument was this: look, anyone who knows anything about entropy, and all of you are now experts on entropy, so you know all about it. Anyone who knows anything about entropy knows there's an intimate connection between entropy and temperature. This we know. So if black holes have an entropy, we also know they have an energy. I can figure out their temperature. Anything with a temperature, like this tungsten bulb, radiates. But black holes don't radiate. They're black. So clearly you're wrong. Okay. However, you know, this argument, while pretty convincing, leaves a possible loophole which Hawking was aware of. And the loophole was this: the statement that black holes are black is a statement made within Einstein's classical theory of relativity. Perhaps, when we do the following, when we try to make relativity, Einstein's general relativity, consistent, add quantum effects to general relativity, perhaps things could change. Hawking, as he says explicitly in his writings on this, didn't believe a word of it, but he thought to be sure he had to convince himself. So he did a calculation. And the calculation he did was the following. He did the simplest quantum calculation with quantum field theory in the presence of a black hole that he could. I won't try to inflict the details on you, but roughly he tried to study the motion of a free quantum field, let's say of electrons or photons, in the presence of a black hole to see how the black hole causes them to react. And to his enormous surprise, this is what he found. He found that when you do the calculation correctly, you find that once you include these quantum effects into the game, you find these black holes are in fact constantly radiating. Every field in the outside of the black hole is being radiated. And in fact, Hawking could find the temperature of the black hole. And by back calculating, he knew the energy of the black hole, he knew the temperature by using that formula T is equal to d by ds. He could back calculate and find the entropy of the black hole. And this is the formula he found. He found that the entropy of a black hole is the speed of light cubed times the area of its event horizon divided by 4, all of this is division, Newton's constant and h bar is Planck's constant. This is a beautiful, beautiful formula. You know, it has all the fundamental constants of nature, C, h bar, g Newton, one formula. And here this formula told us that the entropy of the black hole was proportional to its area, exactly as Bekenstein had foreseen. So you know, this is how physics often works. People who are most sure something is wrong and go try to investigate it because they want to show beyond doubt it's wrong, actually end up finding that they were wrong. That's great. Okay. I remind you that by definition the entropy is the number of states, or more precisely the logarithm, that the exponential of the entropy is the number of states in which a system can be. Just to get some numbers to this, not that it's going to matter for the rest of our talk, if you take a black hole the mass of the sun, the entropy turns out to be of order 10 to the power 78. That's 1 with 78 zeros. And what you're supposed to do to get the number of states in that system is to take the e to the power 1 with 78 zeros. That's a huge number. Okay, that's an absolutely huge number of states that a black hole could possibly be. Okay, excellent. Now we are nearing the end of the talk. Hang on. Is it urgent? Yes.
If you are saying that the area is increasing to a black hole, does that mean that we are just providing it more states?
Yes, that's an excellent question. So, this is the idea. The idea is that the states, which were the uncertainty in which states the cup of tea was in, flow into the uncertainty of the intrinsic uncertainty of which states the black hole can be. It's exactly right. Okay. Now you might think everyone's happy. We've got the second law of thermodynamics, we've got gravity, there's no contradiction, we can go home and be happy. However, Hawking was a stubborn man, and something in this just didn't feel right to him. So he tried to make precise what didn't feel right. And this is what he came up with. You see, at the intuitive level, this doesn't feel right for the following reason. I haven't even told you this. But it turns out that black holes at the classical level are characterized by almost no information. They're conserved charges. The mass and the angular momentum of the black hole, once it's settled down, completely determines the black hole solution. Everything you need to know about the black hole is contained in knowing its mass and its angular momentum. So few numbers, maybe in 4 space-time dimensions, 4 numbers tell you everything there is to know about a black hole. On the other hand, a black hole of the mass of the sun, we're saying that to specify exactly what the state of the black hole is, you have to specify 10 to the power 10 to the power e to the power 10 to the power 78 piece of information. The rough idea is, how can these two things be consistent? How can the classical answer, specifying the black hole requires so little information, be consistent with the quantum answer? Now, this is a fuzzy thing. Hawking tried to take this intuition and make it into a sharp paradox. And the paradox he came up with was the following. Look, consider 2 different black holes. 2 different stars collapsing to form black holes. The initial conditions are organized so that it so happens that both the stars collapse to form black holes of exactly the same mass and exactly the same angular momentum. This needs a little fine-tuning, but of 3 or 4 numbers, very little. Now, the 2 different stars had entirely different compositions. Okay, one of them was lithium rich for some reason. The other one was, argon rich. Okay, whatever. I'm just making this up, it doesn't matter. They have completely different compositions. There's a lot of information in what went into making that star, how all the pressure variations, the density variations in the star before the black hole was formed, that specify the detailed state of that star. Okay, now, as both these stars collapsed, they seem to lead to identical black holes. This seems to indicate that the information of what made up the initial stars has disappeared when the stars collapse to form black holes. Now, you see, Hawking made the following point. He said, in some rough statistical way, probabilistic way, all kinds of things can happen. But at the very basic level of microphysics, disappearance of information is not supposed to be allowed to happen. This goes back to the thing we talked about in the beginning of the talk, when we said that when we described the motion of a gas by specifying all its individual positions and velocities, as time evolves, nothing funny happens. There's no increase of entropy or anything like that. The motions are all completely reversible. You know where the molecules are at later time, you can figure out where they were at the initial time. Okay? And within quantum mechanics, this rough idea is made precise in a set of words which I will not try to describe, but I'll name the words. It says that time evolution is unitary in quantum mechanics. That statement makes a strong version of what I just said precise. That there's exactly as much information in the end state as in the physical initial state. It should never happen in quantum mechanics. It's part of the general structure of quantum mechanics. It should never happen that you, by time evolution, reach a state such that 2 different initial states reach exactly the same final state. That should never be the case. Now, so Hawking's point was, okay, I give up. Bekenstein was correct about the entropies. The second law of thermodynamics is not violated by black holes, but it looks like something more fundamental is violated. It looks like evolution in the presence of black holes is not unitary. The basic rules of quantum mechanics seem to be being violated in black holes. And this, because information is disappearing. And this is Hawking's information paradox. He said, it appears that general relativity and quantum mechanics in the presence of black holes are not consistent. Unitarity a fundamental sacred principle of quantum mechanics without which the whole structure falls down, must be being violated in the presence of black holes. This is the conclusion he reached in 1975, and this statement is the information paradox. And you see, it wasn't arrived at a day. There was all this meandering with the second law of thermodynamics, and this is finally where we reached. Okay. Now, just to make sure we're, that, you know, I want to contrast this information loss, the information loss that Hawking talked about in the presence of a black hole, with another situation in which you might think something similar was happening. Okay? And that's this. Suppose I've got a beaker of water that you put in your house and you let it evaporate. That water has a lot of information in it, the positions of all the water molecules in the beaker. If you used a statistical entropy based, you know, some sort of statistical description of how that evaporation happened, any two different beakers of water with the same temperature and same amount of water would evaporate into quote unquote identical gases. But of course the gases are not really identical. Nobody ever thinks that those gases are really identical. If you follow the water molecules of the gases that you create, they're in different states, because the water molecules of the jars of water that you created were in different states. So we all know that the original description of the water, the two identical descriptions of the water, saying that the same amount of water, same temperature, were just masks. The two different water beakers could be in different detailed states, leading to gases in different detailed states. The evaporation of the water, though it might at first in some crude way have seemed that it leads to identical gases in the end, it doesn't really lead to identical gases. It's just some crude way of describing the system. Okay? I just want to make sure that you understand that this is not what Hawking was saying. You see, because if you go through his calculation, and his calculation is performed in a fundamental theory, as far as he could tell and as far as anyone has been able to tell in a reliable way since then, the description of the radiation that you get out due to the evaporation of the black hole depends only on the classical solution of the black hole. Okay? And so it really seems like the radiation you get out from two different black holes are identical. Different black holes formed from collapse of completely different compositions seem like they're identical. Okay? It doesn't seem like there's much room, and we're going to investigate this in 2 minutes more, much room for these radiation fields actually to be different. But the radiation fields have to be different if unitarity is to be rescued. Without the radiation fields being different, we have different states going to the same states. So something must be giving. What gives? Hawking proposed that quantum mechanics just has to be modified. In fact, he had a famous bet with Preskill, another physicist, saying that eventually we will all agree that quantum mechanics has to be modified because of black holes. Nobody believes that anymore. Hawking himself conceded this bet 7-8 years ago. And he gave Preskill a copy of the Encyclopedia Britannica, which was the agreed on price of the bet. We have to stop.
Can we take a short break? Because
it's like 5 minutes more.
5 minutes more.
Yeah. 5 minutes. Okay. Yeah. The Encyclopedia Britannica to concede this bet. So nobody now believes that quantum mechanics is violated anymore. There are many developments in the study of string theory that make that sound basically very implausible. Okay. So what must be giving? Let's see. Somehow it must be that just like two different black holes that look identical classically are actually as different from each other as two different glasses of water. Now the two different glasses of water that were very different from each other were different because the detailed positions of their molecules was different. So perhaps what's going on here is that the black hole is made up of some sort of atoms of space-time. And when we look carefully enough, we'll see that these atoms are doing different things. That's a natural idea. But one question is, where do these atoms live? If these atoms of space-time live near the singularity, nothing that we know of is violated. However, if they live, Hawking radiation is created from near the horizon, and nothing from inside the black hole can go out. So if we follow the usual rules of classical gravity, no information from near the singularity can reach the event horizon. So if there were atoms of space-time doing their own thing at the singularity, they can do their own thing, but that doesn't help you resolve the information paradox. Because the radiation that comes out comes from the event horizon and will be the same irrespective of what your atoms are doing. So that doesn't help. The next idea is maybe these atoms either live or have effect near the event horizon. And this is a natural idea. Maybe Hawking's calculation was wrong in some way. It got it not completely right and we missed something special. Okay. This is a natural idea, except that if you try to implement it consistent with the way we usually do physics, you can show that it cannot work. In particular, Samir Mathur and a bunch of physicists, Almeri, Marolf, Polchinski and Sully, a few years ago demonstrated as a theorem that assuming the usual structures of physics, of locality and so on, if the kind of thing that would need to happen in order for information to be transmitted into the Hawking radiation, if that happened from the neighborhood of the event horizon, would be such a violent process near the event horizon that it would completely destroy space and time near the event horizon and create what they call the firewall at the event horizon. Okay, so now this is another logical possibility. Okay, this is Polchinski, this is Samir Mathur. Polchinski is a great theoretical physicist who passed away of cancer last year. It's a great man. But okay, their suggestion was that this is what's going on, that local stuff near the event horizon transmits information to the Hawking radiation. Actually, if you do the calculation in detail, you'll find Hawking radiation of two different black holes quite different in detail. But the price you have to pay, as they showed, the price you have to pay, they claimed, would be that space and time near the event horizon has a sort of wall. Something drastic happens. The picture of the black hole that I try to build for you, of this place where you can smoothly sail through the event horizon, bad stuff happens only near the singularity. If what these guys are saying is correct, would have to be totally wrong. It would have to be that even though classically everything is very nice near the singularity, quantum effects make a sort of singularity at the event horizon. Many people claim they believe that this is correct. I personally cannot believe it. It sounds sort of ridiculous to me and sounds very unlikely if this is the case. For instance, if it happens that general relativity, classical general relativity breaks down, where there's no reason within the theory for it to break down, there's no indication within the theory for it to break down, then why does it break down just here? Why doesn't it break down many other places? Why doesn't that contradict the fact that we've experimentally checked general relativity all over the place and it always works? I don't think this is correct. Okay. The third possibility, and this is my second last transparency, it's almost over. The third possibility was suggested by calculations within string theory. There is one completely consistent quantum theory, completely consistent toy model of quantum gravity we have. It's called the ADS-CFT correspondence of string theory. Okay, I will tell you no details about this except for one fact. In this theory, space-time is not a notion that goes into the mathematical formulation of the theory. It's a notion that comes out of the solution of the theory. People like to use the following words to explain this fact. The words that I use are that space-time is emergent. Okay? It's not a fundamental mathematical construct that goes into creating the theory. It comes out of solving the theory in a particular approximation. Okay. So within the ADS-CFT correspondence of string theory, space-time itself and therefore gravity is created in an emergent way. And what these two gentlemen, Kyriakos Papadodimas and Suvrat Raju, both of whom happen to have been my PhD students at some point, what they, I think, quite persuasively argued is that within this one toy model of quantum gravity, which we understand quite well, okay, if you try to understand, you see, the basic rules of physics are the rules of the boundary theory, the theory that you have to solve in order to get space-time. And all the usual properties of physics in space-time come out as emergent properties. So many things look like things are local, like things interact with each other only by touching in space-time. But if you look at the fundamental description of the theory, that fundamental description in terms of quantum variables is inherently extremely non-local. And what these two guys did was to show that the extent of the non-locality was precisely such that would allow them to evade these theorems of Mathur and Polchinski and other people saying that which claimed that if information went out of the black hole, space-time would be destroyed at the event horizon. Within ADS-AFT, these people argued, though they haven't yet perhaps completely shown, that it's possible, in fact it happens, it likely happens, that space-time remains smooth, okay, information comes out, but all this can only happen because because the effective locality of the description of gravity is badly violated in its fundamental description. More precisely, all this can only happen because in these theories, space-time is an emergent notion. It's an emergent notion. The locality of physics in space and time is emergent, and this allows all these things to be consistent with each other. Okay, so this is a discussion that's still going on, and the final word in this discussion has not yet been written. But it may well turn out to be the following. It may well turn out, in fact, if you ask me, I would bet this is what will turn out. Okay, it may well turn out that the final recipe of the story is this. When we understand in some precise way, which we haven't yet done, the answer to the question Hawking posed us, 40 years ago, we will conclude that everything that we believe to be true hangs together only because there's something completely new and unexpected about the theory of quantum gravity, namely that space-time in quantum gravity is an emergent notion. That it's not, locality in space-time is emergent, applies for some variables and violated in other variables. Okay, I know this last part has been very quick and not very intelligible, but anyway, for whatever it's worth, let me just end this by saying the following. You see, the search for the quantum theory of gravity has been greatly inhibited over the last 100 years or so by the fact that we have basically no experiments that give us insight into how gravity behaves at a quantum level. Now, when you lack physical experiments, Einstein taught us you can sometimes get away by doing thought experiments. Hawking in 1975 with his information paradox has done a thought experiment. A thought experiment that has already led us quite far. Okay? And so maybe thought experiments like the one that Hawking showed us about, namely the information paradox, should be taken as the new experiments for our field. Okay? Maybe the information paradox is some sort of experiment whose resolution will provide the key to the nature of quantum gravity. Namely that quantum gravity appears in an emergent way, locality is violated at a fundamental level and so on. Okay, all this is speculation, we don't really know, but I think it's certainly possible. Now just the fact that 45 years after you've asked a question, communities of physicists are still trying to address it, and at least some people, certainly myself, feel that there's a chance that answering this question will lead to great new conceptual breakthroughs in your understanding of the fundamental structures of physics, in this case quantum gravity, is a huge tribute to the person who asked this question. So in this case it's a huge tribute to Stephen Hawking, and perhaps we can end this talk here.